Hello friends, welcome back to my YouTube channel. Today I'm continuing my discussion on tall columns. This is part 2 of my discussion on tall columns, and now I'll be starting my discussion on stress analysis. Analysis of the stresses that get induced in the wall of a typical tall column. And for today's video, I'll be talking about stresses that get induced due to internal pressure, external pressure, and vacuum. My objective is to show you how to get expressions for calculating stresses that are induced due to internal pressure, external pressure, and vacuum. Okay, to begin with, let us first understand which loads are responsible for stresses in the wall of a column. So, which loads act to induce stresses in the wall? So, first you have internal pressure, external pressure, or vacuum. So, these loads they are going to induce longitudinal stresses and circumferential stresses both. The other name for longitudinal stresses are also known as axial stresses, and circumferential stresses they are also known as hoop stresses. And what will be the nature of these stresses? They will be tensile and compressive. Then dead loads induce longitudinal stresses in the wall, and these stresses will be compressive in nature. Wind loads they induce longitudinal stresses, and they are tensile and compressive in nature. Eccentric loads they induce longitudinal stresses, and they are bending stresses. And seismic loads they induce longitudinal stresses, and they are both tensile and compressive. So important loads that have to be considered while designing tall columns I have listed on this slide. I'll be discussing stresses induced to this loads because they will be important for a typical tall column. So internal pressure, external pressure, or vacuum, they are going to induce both longitudinal and circumferential stresses. These are tensile and compressive stresses. Dead loads, they are going to induce longitudinal or axial stresses. They are compressive in nature. Wind loads, they are going to induce longitudinal or axial stresses. They are tensile and compressive in nature. Eccentric loads, they are going to induce longitudinal or axial stresses, and their nature will be bending stresses. These will be bending stresses. Seismic loads they are going to induce longitudinal or axial stresses, and they will be tensile and compressive. So in my coming discussions I'll be covering all these stresses, and today I'll be talking about the stresses, longitudinal and circumferential stresses that are induced due to internal pressure, external pressure, or vacuum. Okay, so let us first talk about circumferential or hoop stresses due to internal pressure. First we will discuss for internal pressure. So now I'm showing a cylinder to you, and let us see if this cylinder is subjected to internal pressure that acts on the wall in this way. So if pressure P is acting on the wall of the cylinder in this way, that is the pressure we are considering pressure acting in radial direction. Pressure acting in radial direction. So what is going to happen? This under the action of this pressure, the cylinder is going to get ruptured in two, you can say, parts. It may get ruptured in two parts like this under the action of this pressure. So and if we call L as length of the cylinder, TS be the thickness of the wall of the cylinder, and DI be its internal diameter. Okay, so under the action of this radial pressure, uh, force F will be causing rupture of the cylinder, and this force will be acting circumferentially, and this force then will be responsible for inducing circumferential or hoop stress in the wall of the column. So under the action of, due to internal pressure, force F comes into picture, and this force is rupturing the cylinder, and uh, under the action of this force, circumferential stress will be getting induced in the wall of the column. So our objective is to know what is this circumferential stress, or how to get an equation for this circumferential stress. Okay, so let us continue. Okay, so again I'm showing you the previous diagram. So pressure P is resulting in force F, which is then causing the rupture of the cell. Okay, so circumferential stress is due to the radial force. We are talking about this radial force, which is resulting from P. P acting in radial direction results in a radial force F. Now this force F, what is it doing? The force F is tending to rupture the cylinder radially. So under the action of force F, under the action of radial force F, the cylinder may get ruptured radially. This force is acting on the area di into L. So the force is acting in this direction. So for its action, the area that will be available for this force is this area L into the internal diameter. So you can just imagine you have this dimension and this dimension. This dimension is L and this dimension is the internal diameter. So force F is acting on this area. So F is acting on this area di into L. I hope this is clear to you. So I'll just show you. So force F is acting in this direction, and for its action, the area available will be this area. Area available will be this area. And what is this area? This area is length of the cylinder into its internal diameter. So F is acting on area. That's why I'm saying F is acting, the force F, radial force is acting on the area di into L. Therefore, if you know this fact, F will be given by this equation. So pressure due to the internal pressure, we have already have understood that F is resulting from P. So P, it acts on area L into P. Di into L. P is acting on the area di into L, and this is resulting in force F. Force F. So it should be, to be more correct, we can say that pressure P in this case is acting on the area di into L, and due to its action we are getting force F, and this force is given by this equation. F is equal to di into L into P. I hope this is clear to you. Let me tell you once again. So we are talking about circumferential stress or hoop stress. Circumferential stress comes into picture due to radial force F, that is resulting from P, the internal pressure. What is the role of force F, the force F may rupture the cylinder radially. Now how force F comes into picture, let us understand. So for that, P is acting, pressure P is acting on the area di into L. So you can understand. So P is acting in radial direction, and for its action the area available will be L into di, and due to this we get force F. So force F will be given as di into L, that is area on which P is acting. So it will be di into L into P. Now this force, the resulting force, is resisted. It is opposed by two areas, and each of this is given by this equation. A is equal to L into Ts. So we are talking about this area, L into Ts, the area that is obtained if you take section of the cylinder. So the area that will be resisting force F is this area and this area. So both have the same equation, L into Ts. There are two areas that will be resisting pressure force F. So each of this area is given as L into Ts. Okay, so if you know the force and if you know the area that is available, or the area on which force is acting, you can easily calculate the stress. Okay, so total area that resists F in this case is 2 times of A, that is 2 into L into Ts. F will be total area that is resisting force F is 2 times of A, that is 2 into L into Ts. Okay. So we have got this equation. We have got equation for F, that is di into L into P, and the area that is resisting this force is 2 into L into Ts. So therefore circumferential stress, let us denote it as Fc. Circumferential stress will be force acting per unit area. Force is di into L into P, and area is 2 into L into Ts. So if you simplify it, you will be getting this equation for Fc. Fc is equal to di into P upon 2 into Ts. So circumferential stress or hoop stress due to internal pressure P will be given by this equation. Internal diameter into pressure divided by 2 into thickness of the shell. The circumferential stress, we just got equation. In case of internal pressure, for internal pressure the stress will be di into P upon 2 into Ts, whereas for external pressure or vacuum, if you have to get the value of, if you have to get the circumferential stress, then what you have to do, you need to replace di in this equation with du, the outer diameter of the shell. So Fc will be then given as P into du by 2s, 2 into Ts, where du, as I said, it is outer diameter of the shell, and if it is an insulated cylinder, insulated vessel, then you need to consider insulation also in that diameter. So du will not only include the outer diameter of the shell, it will also include the diameter of the insulation, and that will come into picture if the column is insulated. Okay, now that was about circumferential stress or the hoop stress. Now let us talk about longitudinal or axial stress. First we'll understand what will be the expression for internal pressure. So for that, again we are considering a cylinder, and now we are talking about pressure that acts in axial direction. So under the action of this pressure, the cylinder may be rupturing in this way, whereas pressure P is acting in axial direction, di is the internal diameter, and ts is the thickness of the cylinder. So this pressure, axial pressure, results in forces, force F, and this force F is then tending to rupture the cylinder in an axial direction. And for this particular situation, we are trying to get an expression for the longitudinal or axial stress. So let us understand. So again, I am showing you the diagram. We are talking about pressure acting in axial direction, which is resulting in force F. So longitudinal stress is due to the axial force F that is resulting from P acting in axial direction, longitudinal or axial stress. The force P, the force F that we are talking about, it is tending to rupture the cylinder in an axial direction. Force F tends to rupture the cylinder axially. Now in this case, uh, pressure P, it will be pressure P is acting, the area available for pressure P for its action will be the cross-sectional area. So you can understand pressure P is acting in this direction, and entire cross-sectional area of the column or of the cylinder will be available for its action. That's why I'm saying pressure P acts on the cross-sectional area. Therefore, the force, axial force that is responsible for rupture will be given by this equation. So force will be pressure into area on which the pressure is acting. So P into pi by 4 into di square. Uh, this force is then restricted by area A. And how is it given? This area is given as pi into d into ts, where d is nothing but di plus ts, that is mean diameter. So if you do an simple you can say analysis, you'll come to know d is di plus do upon 2, which is nothing but di plus ts. So you can say d is the mean diameter, mean of internal and outer diameter. Okay, so the point is force F, which is given by this equation, is resisted by area A, which is given by this equation. A is equal to pi into d into ts, and d itself is di plus ts, which is nothing but the mean diameter of the shell. ठीक है, therefore A will be pi into di plus ts into ts. ठीक है, so under the action of internal pressure, you have we already have got equation for F is equal to P into pi by 4 into di square. Area, we got area on which F is acting is pi into di plus ts into ts. Therefore longitudinal stress will be given as Fa is equal to force acting per unit area. Force is P into pi by 4 into di square, and area is pi into di plus ts into ts. Therefore Fa will be P into di square upon 4 into di plus ts into ts. And continuing with our discussion, we got this equation P into di square upon 4 into di plus ts into ts. Generally, what is the case? Thickness, if you compare thickness with the internal diameter, it is very small. Thickness is very small as compared to diameter. Therefore di plus ts is approximately equal to di. So if you use this modification, you have axial stress Fa is equal to P into di square upon 4 into di into ts. And in the next step, one di will get cancelled, and you will be having Fa is equal to P into di upon 4 into ts. So this is an expression for calculating axial stress or longitudinal stress that is induced due to internal pressure. Now let us talk about what will be the stress due to external pressure or vacuum. So for that, longitudinal stress, we already have got the equation. Fa is equal to P into di upon 4Ts. So how to get it for external pressure? We need to replace di with du. Du is the outer diameter, which includes diameter of the insulation if insulation is there. So in that case, Fa will be P into do upon 4Ts. So do should also include insulation if column is insulated. Okay. So at the end of my discussion, this is the end of my discussion for today's lecture. So we have understood how to get equations for calculating longitudinal stresses and circumferential stresses that are induced due to internal pressure, external pressure, or vacuum. Okay. So with this, I end my discussion for today's video. Thanks for watching. Please subscribe to my channel. Be with me for varieties of discussions on chemical engineering. Do subscribe to my channel. Tell your friends to subscribe to it. Thank you. Thank you for being with me. For now, bye bye. Have a nice day and hope to see you in my next video lecture.